To a computer, a problem is a task to be done. For the computer to perform a task, you must write a program that tells the computer what to do. And to write a program, you must be able to express the task as a sequence of simple steps. No matter how complicated your problem, if you want to solve it, you must be able to specify a starting point, what to do next at each step of the task, and a stopping point when your goal has been achieved. In computer science, the sequence of steps to be followed in the solution of a problem is called an algorithm. Problem solving with the computer is the art of devising algorithms to perform given tasks. It's basically a four-phase process. The first phase is to carefully define the problem. The desired output of the solution must be described in detail. Relevant input must also be identified. Second, the resources that are to be used as parts of the task must be identified. Next, the task must be analyzed and broken down into small steps that are ordered sequentially. Finally, each step is performed or executed to verify that the sequence of steps does in fact solve the problem. Flowcharting is a method of representing algorithms pictorially by using standard symbols. The symbols represent individual steps in a task. Symbols are more understandable than written words. In flowcharts, symbols with rounded ends or corners are called terminal symbols. They mark the beginning or first step and the end of the sequence of steps in the algorithm. Initialization symbols, represented by hexagons, often follow the terminal symbol. They are used to set up beginning conditions such as the values of constants and the starting values of variables. Parallelograms are used to represent general I/O operations. Depending on what's written inside, the symbol may specify input operations or output operations. Rectangles symbolize steps that process data. Arrows connect various block symbols to indicate the sequence in which the steps must be performed. Sometimes the step to be done next depends upon the results of previous actions. Decision diamonds are used to indicate that a choice must be made about which step to do next. Decision diamonds can be used to specify loops, when some process must be done over and over again until some condition is met. And they can be used to specify branches, to indicate alternative steps to be performed next. In each case, the arrows leading out of the decision diamond are labeled to indicate when each sequence of steps is to be used. Now let's look at some examples of flowcharts that represent common algorithms. For our first example, let's consider the problem of multiplying 7 by 4. We must specify an acceptable form for the output, so let's say that the answer must be in a location called sum. It turns out that minicomputers often do not have a multiply operation and perform multiplication using addition. So let's say that the resources we have available include only addition and subtraction operations. And to solve the problem, we must break the task down into steps and order them sequentially. In this case, the steps include start and stop the process, add 7 to sum 4 times, and initialize sum, so that when the process starts, location sum contains 0. When we order these steps sequentially, the first step is the terminal symbol start. Then, in the initialization phase, location sum is set to 0. The task includes 4 additions of 7 to location sum. And finally, the task is terminated. Now that we've covered the problem-solving phases and basic flowchart symbols, go to your workbook for review material and exercises. The workbook will tell you when to return to this program. Now let's look at some examples of algorithms that use decision diamonds and I/O parallelograms. This algorithm for multiplying 7 by 4 is simple and easily represented by a straight sequence of steps. However, if the size of the problem is increased only slightly to, say, multiply 7 by 11, the resulting flowchart loses the brevity that is one of its primary virtues. Even with the long line replaced by labeled connectors, this algorithm requires a lot of repetition. If 7 were multiplied by 100, it would be unmanageable. Decision diamonds allow a few steps to be performed over and over again until a condition is met. This repeated execution of steps is called iteration, and as you can see, it can greatly simplify a flowchart. Let's see how it could work for the problem of multiplying 7 by 11 using addition and subtraction. First, we must determine a condition that can stop the iteration when the multiplication is done. A counter can be used which counts down or decrements towards 0 each time a step is repeated. And when the counter reaches 0, the loop can be broken. So to multiply 7 by 11, a counter can be initialized to 11, the number of times the loop will be repeated. To add 7 to sum each time the loop is performed. Each time the loop is performed, 1 can be subtracted or decremented from the counter. This means that the counter holds the number of iterations still to be done. The decision diamond tests the counter to find out whether it is counted down to 0. If the counter equals 0, the process is done and it's time to stop. If the counter does not equal 0, the process continues by looping back to the addition step. Now let's perform the task step by step to see how this algorithm works using iteration. We begin at the start symbol. Next, location sum is initialized to 0. The counter is initialized to the number of times the loop will be iterated, in this case, 11 times. The first addition puts 7 into sum. 1 is subtracted from the counter, leaving it with 10. And the counter is tested to find out whether it contains 0. Its value is 10, so the answer is no, and we go back to the next addition. Now we add 7 more to sum, so that it contains 14. Subtract 1 from the counter again, and test the counter to find out whether it's 0. No, it's not. So we add another 7 to sum. Take another 1 from counter, and no, it's still not 0. Add another 7. Subtract 1. Test. Add. And after 5 more iterations, the process finally nears the end. We add 7 to sum, bringing its value to 77, which is, of course, 11 times 7. 1 is subtracted from the counter, bringing its value to 0. And now, when we test the value in the counter, it is 0, so we take the yes branch and are out of the loop. Since the task is completed as originally defined, we stop. The final answer, 77, is in location sum. Now let's consider a new problem, which is similar to the last one, but includes input and output. Consider the task of inputting a number, multiplying it by 7, and outputting the result. And suppose that the input will come from a typewriter-like input-output device called a terminal, that addition and subtraction are the available operations, and that the result is to be output to a terminal. How can the flowchart on the left be modified to solve this new problem? First, instead of initializing the counter to 11, which we multiplied by 7 before, we input the number to be multiplied by 7 and put it into the counter. After the value has been decremented to 0 and the result is in sum, the contents of sum are output to the terminal before the process stops. The loop in the middle works the same as it did when we multiplied 11 by 7. We have just seen some examples of flowcharts with decision diamonds and I/O parallelograms. Now, when the tape stops, return to your workbook for practice exercises in the art of problem solving and a discussion of problem solving with a computer.